like what we've done, what you had on the previous exam, so that's kind of good because then you'll see it again. But it's going to be a little more, just one slight complication. And really the only complication is that you have vectors that are in 2 dimensions, and you have to resolve them to the axes, which is stuff that we've done before. You're going to have two-body problems. You'll probably just have one two-body problem on the next exam and a few multiple choice, and then the rest of the stuff will be from the next chapter and the chapter after that as well. So let's see, we're on page 109. We're just going to sort of pick up some stuff that we've been doing regarding 2D forces. Largely, you'll see stuff on an inclined plane, though I'll work some other problems that are similar to, that are 2D problems that are relevant for the exam. But probably you're going to see an inclined plane. They all work out pretty much the same. Um, so this is an inclined plane. Let's imagine that we have an angle here. I don't know, let's say that it's equal to 30 degrees. Uh, when you do these problems, you're first going to just label all the forces. And so on an inclined plane, you'll have several forces that are relevant. These two forces will always be on the inclined plane. Oh, don't worry about the replace lamp thing. They fixed it. It's supposed to be okay. But anyway, so on our inclined plane, these two forces will always be present, the normal force and then also the weight. So a couple things to notice about the normal force and the weight. The normal force, remember, is perpendicular to the surface. It's not always vertical. It doesn't have to be vertical, though that's what we've seen so far. But here, because the surface is slanted, then the normal force is uh, not vertical. It's off axis. And then the weight is towards the center of the Earth. When you do these, we're going to set a coordinate system. So that'll be our x-axis, and this will be our y-axis. I want you to notice on this that if I were to redraw this over here, that I would redraw my force weight. It would be like that, and my normal force would be like that. We had talked about rotated coordinate systems, and that's what we've done here. We've rotated a coordinate system because usually on the inclined plane, most of your forces are either going to be perpendicular or along the inclined plane. And so we'll see that as we're dealing with these, that we'll have forces that either go up or down the inclined plane, or at the very least, we'll accelerate up or down the inclined plane. We're not going to accelerate off in some other direction. So it makes sense here for us to rotate our coordinate system, and we're going to do that with every inclined plane that you encounter. Just a trap that students often fall into is that they forget that this is our negative x direction and this is our positive x direction. That doesn't really make sense, right? Because you're going up the inclined plane, but it's in the negative x direction. And that'll become relevant as we work through some problems. However, notice that if you draw your inclined plane differently, if instead you draw it in this direction, and then we do our coordinate systems, then notice that here, up the inclined plane is now positive x, and down the inclined plane is negative x. Don't try to memorize that. Just draw your coordinate system in the way that we've drawn it here, and then ask yourself, okay, is this to the left of the origin or to the right of the origin? Catherine? It will, yeah. So it will matter what sign it is when you apply Newton's second law as to whether or not the forces are in the negative direction or the positive direction. Yeah, it is important. So make sure that you get those signs right. But I think if you're aware of them, then if you're conscious of that, then you'll get it right. Because you know that this is positive x and that this is negative x. Okay, so just to remind you, positive x, negative x, again, positive y, negative y. Another thing to notice here, people do different things with this, but on your angle for the force weight, I'm going to use this angle, which if you notice this triangle right here, this is a right triangle, so this angle is equal to 90 minus theta. And so I'm always going to measure my angle from the positive x-axis. It makes life a little easier when you start to find your components, because if I find the component here of FWX, FWX is equal to FW cosine of 60, and FWY is equal to FW sine of 60. Hey, Grace? However, I want to show you, because sometimes other people will do this, that is instead of using 60 degrees, they use this angle, which is 30 degrees, which is the same angle as the inclined plane. And notice that here my x and y components become a little bit different. That FWY is equal to FW cosine of 30, and FWX is FW sine of 30. And I'm always going to follow this notation with the cosine being the x component and the sine being the y component, because that's sort of what we've been doing all along. But it will always require you to take this angle as being 90 minus the angle of the inclined plane. So that's really all you have to remember is say whenever I have an inclined plane, the angle for my weight, which is always in the same direction anyway, the angle for my weight is always going to be 90 minus the angle for the inclined plane, which in this case is 30 degrees. Students sometimes get tripped up on that. And if you're looking in other textbooks, or even sometimes in some of the old exam problems, if you see a sine, or excuse me, a cosine for the y component, or a sine for the x component, that's the reason. Because instead of using 90 minus theta, we're using actually theta. Other textbooks will sometimes do that, but just be aware of it. As far as me, I'm going to always stick to this cosine sine notation. Y'all follow me? How these are equal to sine of 60 is equal to cosine of 30. So these are the same statements. They're just, you know, different. The reason here is that this angle, this is the adjacent side, so it's cosine. This is the opposite side, so it's sine. Yeah? Okay. Students sometimes get messed up with that. They get messed up with the coordinates. They sometimes get messed up with the angle, how you do the angle. But again, as with the coordinates, just be conscious of that fact that when you're setting up your angles, that you take 90 minus the angle on your inclined plane. Okay, let's work a problem because yeah, let's just work. Well, no, let me make one other point. So once you set all this up, you resolve your vectors. So first, we draw the forces. Second, we do a free body diagram. That's this. This is our free body diagram. It just means that we take away the picture and we just draw a diagram that only has the force vectors on it. Third, and this is a step that we haven't done yet, is we resolve the vectors, meaning prior to today we haven't done this. We resolve any vectors that are not on axis. Usually that's just going to be the force weight vector. Usually that'll be the only vector that we're dealing with that's not on axis. And then after that, we apply Newton's second law. For all bodies, just like we've done before, just like you did on the exam. It's going to be very similar to that problem, actually, like you had on the exam. And then 5, you just solve. You solve a system of equations, or you do whatever you need to do with the algebra to get to what it is that you're looking for. But your procedure will always be the same. You might choose to combine these 2 steps. You might even choose to combine all the first 3 of these steps. Like just skip straight ahead so that you've resolved all your vectors. But you're always going to follow these steps. You'll need to apply Newton's second law, write out your equations, and you'll see when you get your exams back. If you wrote your equations correctly, but then you just completely messed up solving them, I didn't count off, just maybe 2 or 3 points. So you'll need to really focus on this part where you get your equations correctly written, and then you solve that. I don't put a whole lot of weight in the solution, but writing the equations is very important. Let's do an example. So this is from an MCAT problem. Inclined plane's pretty big on MCAT. I don't think I have any pre-meds, though. Do I have pre-meds in here? A couple, yeah. So for the inclined plane, if you have an inclined plane, you need to know it backwards and forwards. MCAT changes time to time. So let's say that I have a box on an inclined plane. Say that it has a mass equal to 10 kilograms. And I want to know what force must be applied up the inclined plane so that the box is stationary. So what I'm saying is we have a force that is acting in that direction. I want to know what that force is in order for it to remain stationary. The other forces that I have are weight, Fw, and then my normal force. So take just a minute to get a head start. Draw your coordinate system. Remember our coordinate system is x-axis, y-axis. Go ahead and draw your coordinate system. Determine what your angles are. I'm going to tell you that this angle is 30 degrees. Draw your coordinate system. Let's go ahead and draw your free body diagram now too, where you label all the vectors. Is that a dog? Who is that? Probably the president's dog. All right. What was I saying? Oh, free body diagram. Resolve your vectors into their x and y components. Let me give you just a minute. If you get that far, go ahead and apply Newton's second law. Should have something similar to this. Label all my forces. Recognize my coordinate system. It's better to rotate it. You're always going to rotate it. Draw it again where I sort of rotate it back into regular space, but I keep my forces as they are on the coordinate system. F is here, Fn is here, Fw is some angle below the axis, 90 minus 30. That angle is equal to 60. And I'm going to resolve my vectors. Fwx is, what is x? The x component of the force? It's cosine 60, right? So my Fwx is cosine 60. Fw times cosine 60. Fwy is Fw times sine of 60. And this is a static problem. It says that it's stationary up here in the problem. That means the acceleration in the x direction equals 0, and the acceleration in the y direction equals 0. Of course, that would also be true if it had constant velocity. So if it had constant velocity, that also means the acceleration is 0. But in particular, this is a statics problem because it's stationary. And now I apply Newton's second law. So this is the final step. I say the sum of the forces in the x direction equals max, which is equal to 0. And the sum of the forces in the y direction equals may, which is going to equal to 0. For our inclined plane problems, only for inclined plane problems, ay is always equal to 0 in the y direction. Because if it wasn't, it would fly off the inclined plane. It would be a different kind of problem. X direction, you might see some that are 0 or non-zero. It can be accelerating up or down the inclined plane. But in this case, it's stationary. Probably you're going to have a statics problem. But we'll see both types. So now are some of the forces in the x, just like we've done before. We've done this, where I say this force is positive x minus this force. So I say Fw cosine 60 minus F equals 0. And then I can do it in the y too. Fn minus Fw sine 60. That's also equal to 0. And now we solve. We're looking for F, right? This one's fairly straightforward. On your exam, yours will be more complicated. You'll have two bodies and you'll have some various factors that are coming into play like friction. But this one's fairly straightforward. I just solved this for F. F is equal to FW cosine 60. Cosine 60, that's a half, right? Yeah, so that's equal to 50. 100 newtons times a half, so 50 newtons. That's the answer. Again, this one's fairly simple, but it's the same procedure for even the more complicated ones. It's simple because it doesn't have any friction and it doesn't have a second body. And also not accelerating it makes it a little simpler as well. Okay? Let's step back through the steps, or go back through the steps, and we'll move on to a more complicated problem. Label the forces, figure out what's going on, draw my coordinate system, figure out the angle here and how it applies to the force weight. Right? Then resolve my vectors, which is sort of our new step here that we haven't done before. Resolve my force vectors into their x and y components, and then apply Newton's second law. Realizing my acceleration is 0 in both directions, some of the forces in the x, some of the forces in the y. I wrote out both equations here. I didn't really need to. And if you had a problem like this, you might say, well, I don't even need to deal with the y because it doesn't even have what I need to know. But figure out what is that force. You will have some problems where you need to know the normal force because, friction is dependent upon the normal force. And in that case, you would solve this for the friction. And it's, 87 newtons or whatever. Okay, that one's easy enough so far? Yeah, maybe, maybe not. Okay, let's do another one. Um, let's try this clicker question first, actually. You'll probably see a question like this. This is an inclined plane. Hold on, let me make a change here. What is this? No, I'm going to let you go with it. So let me zoom out. So it's an inclined plane. There are four equations here, and I want you to tell me which one is actually correct. Some of these equations are correct, and some are incorrect. You might just want to write out all the equations, and then you can pick out the ones that are correct or incorrect. Does everybody have the book in front of me? I know you probably can't see these equations. Actually, you have it in front of you? Yeah. Okay, good. Okay, looking pretty good. Well, about two-thirds of you have the right answer, and about two-thirds of you have the wrong answer. So why don't you ask your neighbor what they think. You want to look closely. If I have a force that's listed in the equation that's in the y direction, and then also a force in the x direction, that can't be right because our x and our y forces, they're independent of one another. They don't affect one another mathematically. So if I have a force that's in one in the x, one in the y, then you know that equation is not correct. Right, I'm going to stop at 1:55, just 5 more seconds. 55. Okay, good. C is right. Let's look at them. Actually, no, I'm going to write all the equations, similar to what we've been doing. I'm going to go ahead and resolve FW here. I'm combining those first three steps. This is FW sine of 60 and FW cosine of 60. It says it's accelerating up the inclined plane, so AX is in that direction. Notice that's positive AX. So I would have Fn minus Fw sine of 60 equals to 0 because AY equals 0. And then in the x direction, I have F minus Fw cosine 60 equals MAX. I can't set that to 0 because it's accelerating. So let's look at these. Fn minus F, that's not correct because F is in the x direction, Fn is in the y direction. So they're not in the same equation. They're independent of one another. This next one, Fn minus Fw sine 30 equals MAX. That's not correct for a couple of reasons. Fn and AX have a y component force and an x acceleration, so that they're not related. And then this Fw sine 30, this is the x component of the weight. And so it's also not related to the normal force. Why is it the x component? It has a sign, right? So what's up with that? It's the 30 degrees. So the sine of 30, that's the x component is the opposite side from the 30-degree angle. You won't see something like this. Well, no, you could discern that this was the incorrect equation just from these two. But then also this is the x component of the weight. This third one was correct. Fw sine 60 equals our normal force. That's straight from there. And D is incorrect because the force weight is not equal to the normal force, but a component of the weight is. Let's see. Let's try this. This is not an inclined plane problem, but it is a force vector, a 2D force. I think that, yeah, so you will have friction on this next exam, and I'll show you some examples maybe today, maybe not, or we'll probably start one. But remember with our friction, we have kinetic and static friction, and both of those are equal to this coefficient times the normal force. That will become important in some of our other problems as we work through them. Okay, let's start with this one. So this is a good indicator of what you would have on your exam, something similar to this. And there are other variations of this that include an inclined plane or don't include an inclined plane. But what you have here are two objects. You have the object A and the object B, and you want to treat them separately, kind of like you did on the exam, and figure out the forces. Let's see, what are we looking for? The maximum weight of block A so that this system remains at rest. And also, I want you to think about this. These ropes, we're imagining that they're rigid so they don't change shape. I know that's not realistic, but you could have some rigid rods holding it in place that are massless. And also, if I look at the forces that are related to A, I can imagine that they are all right here. So I'd have a force in this direction, a force in this direction, and a force in this direction. That would be the block of weight, the weight of mass A, or block A. All right, so why don't you go ahead and start on this. I'll jump in there. I don't think we're going to finish it today, but let's try to at least get the vector diagrams drawn. You're going to have two vector diagrams. You'll have one for block B, and then you'll have one for block A. The one for block A I've mostly drawn for you here. I have drawn for you, actually, but you'll need to set up your coordinate system and think about how that's going to look. Think about the forces that are acting on block B as well, and draw a vector diagram labeling all those forces. So two vector diagrams, just like on the exam. You had two blocks, two vector diagrams. The only difference here is that one of our forces is off axis by friction involved. Give you a couple minutes head start. I'll jump in. Think about all the forces that are involved and be careful to keep proper subscripts. How many forces do I have on block B? I have 1, 2, 3, or 4 forces on block B. I have 4 forces. Let's think about what they are. Of course, I have the weight because it has mass. It's sitting on a surface, so it has a what kind of force? Okay, it has, okay, good. It has a frictional force and a normal force as well. And I have this tension because I have this rod or rope or whatever pulling on it in this direction. Those are all the forces that we have. We have 4 forces. They're all on axis, which is nice. Fn. I'm not going to subscript that because it's the only normal force in the whole system. The other object doesn't have a normal force. I have Fs because it's not moving. I have FWB. I am going to label it with a B because there's another object that has a weight, block A. And then I have FT. I'm going to label this FT1 for now because there will be a second tension. Now think about this other one. So I've already drawn them. But I have 3 forces here. What will we call this force? FT1, right. Just like in your in the exam, the tension in this rope is the tension in this rope. And it's going to be the same here as it is here. So this force is going to be FT1. This force will be FW, not just FW, but FWA. We'll need to write as FWA. And then this is a different tension. It has a different tension from here. I know that it's static, right? It's sort of like that previous problem with Big Buck Bunny, that if I have these two forces, I know that this force has to be different because it's going to be equal but opposite to the sum of these two forces. So this tension and this tension, they have to be different if this is a static situation. So let me label those. This one is FT1. I'm going to call this FT2, and then this is FWA. Okay, now I'm not going to worry about redrawing the one on the left, but let's redraw the one on the right because it has a force vector that is not on axis. So this is FT1. This is going to be FT2. I give the angle here, sine of 30. Now remember with the inclined plane we took 90 minus that angle, but here we don't have that. The angles measure from the x-axis, so we keep the angle as it's written. Remember, you only do that with the inclined plane. FT2 sine 30, FT2 cosine 30, and then we have FWA. Okay, our next step is to write out our equations. Since we have two bodies and two axes, we can write a system of four equations. And then from that, we'll need to figure out what's known and what's unknown. If you write that system of four equations, you're going to get most of the credit. If you write them correctly and put them right there so I can see them as you've written them, you're going to get most of the credit on the problem. So if you can get up to this point and just write the equations next correctly, most of the credit. Although this one will resolve us to solve that system of equations. Yeah, right here, you mean? Or over here. Okay, I choose where to draw my coordinate system. I can draw it wherever I want. And so I chose to draw the coordinate system over here because when I draw it there, it puts FWA and FT1 on either the X or Y axis. Okay. When I gave this on a test. I actually told the students that imagine all the forces originating here, and this weight is coming down. But the reason that I draw it in this way is because I choose my coordinate system to be here because it just puts these two forces onto the X or Y axis. I'm not sure if I answered your question. Okay. Oh, right here. In order, that's a good question. She asked why didn't I draw FT2 like this, right? Well, because I have to resolve it onto the X or Y axes in order to write the equations for Newton's second law. Whenever you write those equations, you can't have a force vector that's off axis somewhere. So this is that third or fourth step, I forget the number was, of resolving the force vectors. Right, so you must resolve the force vectors when you're doing these problems. You can't have a force vector that's sticking off in one of the quadrants. All right, so let's write the equations. All right, the ones on the left first. The sum of the forces in the X equals Ft1 minus Fs. That's equal to 0. Sum of the forces in the Y, Fn minus Fwb. That's equal to 0. I'm looking at the Y-axis here, looking at the X-axis here, summing up the forces, setting them equal to 0 because it's a static situation. I do the same thing over here. Sum of the forces in the X, Ft2 cosine 30 minus Ft1, and sum of the forces in the Y, Ft2 sine 30 minus Fwa. All right. Some extra equations over here that we'll use next time when we come together is that Fs less than or equal to mu s times the normal force. And then also the weight of these objects is equal to their mass times g. So really I have a system of 6 equations, but I'm just going to sort of tuck these off to the side. And then as I figure out things, I'll be able to fill in some unknowns. Because right now we got a whole heck of a lot of unknowns. But if I can figure out my normal force, I can make some substitution for the static frictional force. We'll come back to this on Monday, and we'll deal with how to solve this, and I'll show you some other ways that you can solve it. We'll solve it through substitution like we did, but then we'll solve it by a different method, which you'll be able to do for extra credit on the next exam. By the way, there will be several opportunities for extra credit coming up. We're going to have a food drive on campus, and we'll participate in that sort of collectively as an entire class. And there'll be some opportunity for extra credit with that. We'll have an assessment later in the semester. It's just sort of it's for a campus thing, and that'll be an opportunity for extra credit. And then also on your test, I will include some bonus point type questions. Okay, so I just want to let you know that if you didn't do well on this last exam, that there will be opportunities to pick up some extra credit in the class. But there's still a lot of exams. You know, do well in these next 2 exams and the final, and it can really change your letter grade by a couple of letter grades or sometimes even more. All right, I'm going to hand back the Scantron first, or the form, I'm gonna show you the solutions up here. So when you get it, if you want to go through and grade it yourself, you can. I haven't posted the video yet, but I have posted the actual exam.